Our project is about real-time image transformations and encryption on the Nexus 7 FPGA. The original plan was to have a camera inputting images to our FPGA. We would then use switches on the FPGA to select between various transformations, and the transformed image would be outputted to a VGA display. In the end, we were able to successfully simulate the image transformations in encryption. We were also able to synthesize an interface between the camera, the VGA, and the onboard frame buffer. We chose to do image processing because image processing has a variety of applications in developing technologies. In addition, the hardware-level parallelism on an FPGA allows us to perform such image transformations much faster than on multi-purpose processors. We currently have the ability to perform 10 image transformations. We are also able to encrypt images with 32-bit keys. On the FPGA, we are able to interface between the camera, the FPGA, and the VGA output using a dual-port block RAM buffer.
So the first technical side we're going to look at here is the overall data pipeline of the FPGA and the Verilog we use to implement this data pipeline. So you can see here it's a very straightforward data pipeline. We start with the camera and apply pixel-wise downsampling on every pixel being read in and store these pixels in a frame buffer. On the output side of this frame buffer, we apply transformations and send it straight to our VGA output. So looking at the Verilog, you can see we took a very modular approach to this, and everything is handled within its own modules. If we look at the schematic here, you can see it is, the synthesized version reflects this modular approach. On the left side here, we have all of our camera inputs. We have our VSync, href, and data, and it goes straight into our camera read module. And this is going to do some pre-processing on the camera data, and it's going to output a 12-bit pixel value, which goes directly to our BRAM. And the address for this BRAM is going to be controlled by the BRAM controller. And from the BRAM, we go straight to the VGA out, and the timing here is going to be controlled by our VGA interface down here. So step one is the camera, for which we are using an OV7670 camera, which outputs 480 by 640 in RGB565. An important detail here is our data output is synchronized with the camera's internal clock, not our system clock. And our driver code here is borrowed, and it reads the camera data 1 pixel at a time, which is also an important detail. So here's, again, some brief wiring of the camera. We are using the FPGA's JA and JB ports. So step 1.5, as I call it, is the pixel-wise downsampling, where we're converted from RGB565 to RGB444. The reason we're doing this, one, is that the RGB565 is too large for the block RAM, and two is that the VGA on the Nexus A7 only has 4-bit output values anyways. So you can see to do this, we're simply taking the 4 most significant bits of each pixel, or each color channel, and setting that as our RGB444. Very simple. Step 2 is the frame buffer. So let's start with why are we doing this? 2 reasons. So one is for displaying the image. I mentioned earlier that the camera has its own clock. The VGA has a different clock, and so we need to use a buffer so that these can work in harmony. And the second reason is for transformation. So we have some transformations such as convolutions that require knowledge of local pixels, and so we need to use memory to perform these operations. And we're implementing this using a FIFO style buffer in block RAM. So what you can see here is the block RAM instantiation. So we basically have dual port block RAM here. So on the right side, on the read side, which is going to be from the VGA, synchronized with the VGA clock, basically just setting data out to equal the memory of the read address. Again, this is controlled by the VGA controller. And on the right side, this is going to be controlled by the block RAM controller, the address, and the write enable. So yeah, why are we using BRAM? Again, the DDR is complicated, and there's enough space in the block RAM for 1 frame in RGB444 format, so the DDR RAM isn't necessary. And again, we have the write controller, and this is implemented as a finite state machine. So we're going to look at the Verilog for this real quick, and you can see we have 4 states, but all these states are going to modify is the write enable and write address. And these are going to work in harmony with the camera read module to determine the address to which a frame should get written, or a pixel should get written inside the block RAM. So our step 3 in this pipeline is the transformations, which unfortunately we were not able to push to the FPGA. However, this was the vision for how we wanted to implement this. We want it to lie right between the frame buffer and the VGA output and apply pixel-wise transformations in between these two blocks. And the transformation would be selected using the FPGA switches. And the final step here is the VGA output, and it operates again with a 25 megahertz clock. And so we need to, with this clock signal, we need to read from the block RAM while coordinating the H-sync and V-sync signals, and of course the address from which we want to read inside of block RAM. And to summarize all this timing stuff, again, we have 3 different clock signals going. So the one on the left here is the pixel clock from the camera. The one on the right is the VGA clock, which is 25 megahertz, and we have our master system clock at 100 megahertz.
The second part of our project involves the actual image transformations. Ideally, this process would have been done on the FPGA. However, we did come up with a rather interesting and complex simulator that's able to read images off of your computer and export them to your desired locations, which we will showcase later in a demo. Throughout the project, we continually added transformations that we wanted to do. We settled on approximately 10 of them that we found were functioning well and still interesting to use. These range from changing brightnesses to changing color scaling, as well as some more interesting ones that we discovered through some debugging, such as our trip transformation, as well as more complex ones that use interesting matrices like blurring. Now we're going to show you a demo of how to actually run the simulator. Hopefully you'll get a good understanding of how you can change this process around for a variety of different transformations and add to it. Here we already have Vivado open at a new project with all necessary files imported. First, you want to check that your file locations are correct for both where you want to import the file from and where you would like the file to be exported from. After checking this, you'll want to move to the parameter file where you can select which operation you'd like to do. Here, we'll be selecting the grayscale operation. Here you can see we uncomment that and save our file and ensure that all other operations are still commented out. You then can run the behavioral simulation, ensure that all files are saved, and allow the simulation to run.
A few moments later.
You can see that the file has now been generated, and you can compare. We've successfully created a grayscale image of our original image. Hopefully that demo was helpful. Now we'll be able to show you a variety of different transformations that we were able to achieve, such as here the grayscaling that you saw in the demo, as well as red scaling, green scaling, and blue scaling. Some of the more advanced processes we came up with were things like this, where you can decrease the brightness, increase the brightness, thresholding, and color inversion. Now the past set of transformations that I've just shown are all done pixel by pixel. And while they're all interesting, we want to create more complex transformations. To do so, we need to use something called convolution matrices. Here, we're showing 2 basic ones, sharpening and blurring. We actually utilize the blurring one in our process and have attempted to create a sharpening one, but fall into a lot of the similar issues that many people fall into with sharpening matrices. The main issue is that they get too bright. So how do these moving frames actually work? So what you do is you first identify the pixel that you want to operate on. So here we have that pixel identified in red, and we also want to take into account all the pixels around it. So here we have 9 additional pixels, which you'll notice will correspond to these matrices and the weightings that will apply to them. And as you're processing your image, you want to go through pixel by pixel and operate on all of them. And as you do something like this, you can take into account the surrounding pixels and achieve something more interesting, such as here, a blurring. Now, while all of these past transformations are working and are interesting, some of the more unique experiences that we had throughout this process was when one of our transformations didn't work during the debugging process. Now, this could lead to a lot of strange and interesting transformations and images that got produced, and a lot of them were thrown away, but some of them were still pretty interesting. Such as this, which was an attempt at grayscaling, which created more of just a static effect where you lose sight of the birds. Or here again, during the sharpening, essentially the same thing, but now with crazy colors, and it's super interesting to look at. Some people even think that you can find a zebra in here, but I'll leave that up to you. Or finally, you can get something that looks pretty unique. Now here we were attempting to do a sharpening, but this obviously isn't a sharp image. This is a colorful image. It's something interesting, and it actually kind of looks like art. So we've decided to keep this, and we've denoted it our trip transformation. And it just goes to show you that even when a project isn't fully working and the debugging process can be stressful, you can still find cool and interesting things that you can use in your project. Aside from these interesting transformations, we've also implemented a rather interesting processing technique known as parallelization. Parallelization allows for us to operate on multiple pixels at the same time, which ideally should increase the speed of our program. This should allow us to get us transformations quicker and operate on larger images in the same amount of time as smaller images that are not operating with parallelization. Now, of course, there's no such thing as a free lunch, so we do have to pay the initial cost of actually loading the full image into that vector, which you can see here represented by the nested for loop. However, we achieve our later gains by operating on those 2 pixels at the same time and can actually scale this up to operate on more and more pixels at the same time. While this does increase our speed, the trade-off now is that we have to allocate more memory because we have to keep the image stored while also doing all of these operations.
Okay, I'll be talking about the image encryption real quick about our EC551 final project. So basically, we have these 4 important modules within our encryption module. So the pseudo random number generator, the encryption, the symmetric key encryption and decryption algorithms, and as well as displaying the 32-bit key that we chose as size for the blocks of encryption and displaying that key on the 7-segment display. So we begin here with the random number generator. We implemented a linear feedback shift register, and this is straight from the lecture 13 implementation of the slides. Basically here we have a series of flops and the tap coefficients in which the values are fed back into the flops for a more random value at each clock cycle. We also have our symmetric key encryption algorithms, and I chose 2 for this final project implementation. And I chose these 2 algorithms just because of their difference in implementation and pros and cons. So with the electronic codebook encryption, it's very simple. It's a simple algorithm. You could parallelize encryption and decryption, but it also has like the drawback of being repetitive, so attackers will be able to find out the pattern. And you have cipher block chaining encryption algorithm, which takes in a random initialization vector, which creates that randomness to be able to obfuscate the ciphertext or the cipher blocks if it is being chained per every block of this of the plain text. Its pro is its parallelized decryption, but its encryption is not parallel because of the dependency between both multiple blocks. So why does encryption matter? So for imaging and image processing, imagine you have 2 clients and they're talking to each other over a video call like Zoom, Skype, FaceTime, whatsoever. Imagine that is not encrypted. You could have a person that intercepts or manipulates those packets in the medium and be able to, I guess, find out what they look like, where they are, and who are they talking to. This is a security hazard, security vulnerability within like the world of like streaming data and communication. And we want to make sure that both or all users have some sense of confidentiality with their data and that they know it's secured. And the images to the right shows these 2 lovely parrots being encrypted with both algorithms. So the middle image represents the electronic codebook algorithm. You can see here that some of the blocks have repetition, but it still has a distorted figure to it. And at the bottom here, you could see that there is some sort of outline, but not very entirely recognizable. That is 2 parrots. This is from the CBC algorithm because of the dependency in chaining the cipher blocks for each sequential block. And finally, here comes Verilog. The ECP encryption has a very simple implementation for our case because we use an XOR implementation for each bit of the buffer, and specifically our buffer was 48 bytes since 48 bits, excuse me, for the buffer size, because we take in 2 pixels and each pixel has an RGB 888 configuration, which basically makes each pixel 24 bytes or 24 bits, excuse me, 24 bits in size. So 2 pixels, 48 bits in size. And our CBC encryption has a more involved approach where we have an intermediate XOR operation where it takes the previous buffer, ciphertext buffer, and XORs it with the current buffer that is about to be encrypted with the key and then that current encrypted ciphertext is then stored as the previous for the next block.
So this concludes our semester-long project. Thank you so much for watching, and we hope you enjoyed.